barium chloride reacts with sodium sulfate, and we're given this chemical reaction here. What would you see when this reaction is carried out? A. Blue solution turns colorless. B. Effervescence. C. No visible change. Or D. White precipitate. Now let's check the chemical reaction. So we have here barium chloride reacts with sodium sulfate, and it produces barium sulfate and sodium chloride. And barium sulfate here is an insoluble white solid which is formed from the reaction between barium chloride and sodium sulfate. Therefore, the answer here should be letter D, white precipitate. And the white precipitate observed here is barium sulfate. What is the ionic equation of this reaction? So given the same reaction, barium chloride reacts with sodium sulfate. We're given here the molecular equation of the reaction. Now, to write the net ionic equation of this, we need to write the full ionic equation first. So all strong electrolytes or soluble salts are written as dissociated ions. So this reaction would become, okay, barium, the charge is 2 plus, and then we dissociate barium chloride. So this is plus chlorine ions, and that is 2 moles of that. Then the sodium sulfate, so that is 2 Na plus, and then the sulfate, this is SO4 minus 2. So 4 minus 2. Okay, and this forms barium sulfate. So we just leave the barium sulfate as it is, since it is solid, and then we dissociate sodium chloride. So this is 2 Na plus and chlorine, 2 moles of chlorine ions. Now we just identify the spectator ions, and they are the sodium ion and the chlorine ions, as they appear on both sides unchanged. So we cancel them out. So we're left with barium ion, then barium, oh no, we have sulfate. We still have this one. So sulfate ion, and then barium sulfate. Right, now this is the ionic equation of the reaction. Therefore, the answer here is letter C. And take note here that barium and sulfate ions are the ions that react. They combine to form the insoluble solid barium sulfate. Alright, letter C, the same problem. Reaction between barium chloride with sodium sulfate. What is the maximum mass of barium sulfate that could be produced from 0.500 gram of barium chloride in this reaction? So we are asked for the maximum mass of barium sulfate that would be produced given the mass of barium chloride. All right, so we start with, to solve this, we start with the given values. So the given value here is the mass of barium chloride. We just have to divide this by its molar mass, which is given here, to solve for the number of moles of barium chloride. So we divide this by 208.3 grams per mole barium chloride. So the gram unit here cancels out, then we're left with the mole unit. So using your calculator, this would give us a value of 2.4 times 10 to the negative 3, or 0.00240 mole barium chloride. Now, since we are interested in finding the mass of barium sulfate that will be produced from the given mass of barium chloride, and we've already solved for the number of moles of barium chloride, we just need to get the molar ratio and multiply to the number of moles of barium chloride. Okay, let's check the chemical reaction here for barium chloride and barium sulfate. So the ratio is just 1:1. Okay, 1 mole of barium chloride is to 1 mole of barium sulfate. So we can just do this 0.020240 mole barium chloride times 1 mole of barium sulfate per 1 mole of barium chloride. So now we have the number of moles of barium chloride, which is just equal to the number of moles of barium chloride, or barium sulfate then, which is equal to the number of moles of barium chloride. So that is also equal to 0.0240 mole barium sulfate. So now we already have the number of moles of barium sulfate. Now we can solve for the mass of barium sulfate by multiplying that to the molar mass of barium sulfate. So this is 0.00240 mole barium sulfate times molar mass, this one, 233.4 grams barium sulfate per 1 mole of barium sulfate. Right. So the mole unit here cancels out and we're left with grams barium sulfate. And this would give us 0.560 gram barium sulfate. So this is our final answer. So the answer here is letter C. Okay, the same problem, but another question. What is the atomic economy by mass for the formation of barium sulfate in this reaction? So how do we solve atom economy? Atom economy is just equal to the mass of desired product divided by the total mass of reactants times 100%. So we're given here the mass of desired product of barium sulfate, which is 233.4, divided by the total mass of reactants. Reactants are barium chloride and sodium sulfate. So this is 208.3 plus 142.1 times 100%. And this would give us an atom economy which is equal to 66.6%. So the answer here is letter C. Which of these forms of carbon does not contain the localized electrons? A, diamond, B, C60 fullerene, C, graphene, or D, graphite? The answer here should be diamond. Because diamond here, each carbon atom has 4 single covalent bonds, from sp2 hybridization in a tetrahedral structure. So there are no delocalized electrons in diamond, so it does not conduct electricity. While these three here, C60 fullerene, graphene, and graphite, they have the localized electrons from sp2 hybridized carbon atoms, thus allowing some electrical conductivity. So the answer here should be letter A, diamond. Which of these molecules is polar? OF2, BF2, CF2, or PF5. So let's analyze each of the molecules here. Okay, so we have OF2, or oxygen difluoride. The structure of this one is bent or V-shaped. So this is a V-shaped molecule due to two lone pairs of oxygen. Then the oxygen fluorine bonds here are polar because of the asymmetrical shape, and the dipoles don't cancel. So overall, this molecule is polar. So the answer here should be letter A. Let's take a look at the other choices, BF3, CF4, and PF5. These three molecules, they are symmetrical, and their bond dipoles cancel out, thus making them nonpolar. So the one that is polar here is OF2, letter A, or oxygen difluoride. Which species has its correct shape and bond angle shown? So we're given here 4 species, CH3 ion, NH3, NH4 ion, and water. So let's take a look at each one of them. CH3 ion, or the methyl cation, its central carbon, this one, has 3 bonding pairs and no lone pairs. Therefore, it has a trigonal planar shape with bond angle 120 degrees. And for NH3, this is pyramidal, but the bond angle here shouldn't be 109.5 degrees, but 107 degrees. And for ammonium ion, or NH4 plus, this should be tetrahedral, not square planar. So the shape should be tetrahedral with bond angle 109.5 degrees. And for water, water is bent or V-shaped with bond angle 104.5 degrees. So the species here that has the correct shape and bond angle is letter A, this one, the methyl ion. So the answer should be letter A. Some equations for reactions used in reforming crude oil fractions are shown. Which equation is not balanced? So let's check each of the choices here. So we have letter A. Okay. So we have 1, 2, 3, 4, 5, 6, 7 carbons. Here 1, 2, 3, 4, 5, 6, 7 carbons. So this one, this equation here represents a correctly balanced isomerization. So letter A is balance. We're looking for not balance. How about letter B? So we have 1, 2, 3, 4, 5, 6, 7 carbons, and here 1, 2, 3, 4, 5, 6, 7 carbons plus H2. So that means this is balanced. And for letter C, we have 6, 7, okay, 6, and we have double bonds, but we have 3 H2 here. So that means this is also correctly balanced. And for letter D, we have 1, 2, 3, 4, 5, 6, 7. We have 1, 2, 3, 4, 5, 6. So 7 plus 3H2. So in this case, this one isn't balanced. So letter D is the one that isn't balanced. So the answer here should be letter D, because the number of hydrogens are not equal. A pure alkane fuel is burned in air. Which substance is not a possible combustion product? A. H2, B. H2O, C. CO, or D. Cl2. Now take note that when an alkane burns in air, the possible combustion products are, for complete combustion, the products would be carbon dioxide and water, and for incomplete combustion, the products are carbon monoxide and water, and sometimes just carbon soot. So among the choices here, hydrogen gas, this one, H2, is not produced in any type of combustion of an alkane. It would actually burn and not form. So the answer here should be hydrogen gas, letter A. Which polymer? The polymers shown are all made from single monomers. Which polymer is made from a monomer that has geometric isomers? So what are geometric isomers? Geometric isomers, or what we call as the EZ isomerism. This one is EZ isomerism is a type of geometric or configurational isomerism that occurs in alkanes. So these are all the molecular structures of alkanes. And this where there is restricted rotation around a double bond of carbon. And each carbon of the double bond has two different constituents. And this is based on the priority rules for determining which substituents are higher priority. So if higher priority groups are on the same side, so on the same side of the double bond, then the isomer is Z, or from the German word zusammen, or together. And if the higher priority groups are on opposite sides of the double bond, the isomer is E, or opposite. And how do I pronounce that? Entgegen. Now let's take a look at the four given structures here. So this one, letter A, it doesn't have an easy isomers, as well as this one, see, and letter C, as well as letter C. So the only polymer here that is made from a monomer that has geometric isomers or easy isomers is letter D. So the answer here is letter D. This question is about the element chlorine. Give the electronic configuration using the SPDF notation for a chlorine atom in the ground state. So chlorine atom has 17 electrons because its atomic number is equal to 17. So it has 7 electrons. So we fill the order from lowest to highest energy. So 1s, 2s, 2p, 3s, 3p. So let's fill that in. So the s orbital will just fill in 2 electrons, and then p, 6, and then s2. So 6, 10, 11, 12, we have 5 more. So we have 3p. 3p5. Therefore, the electronic configuration of chlorine is 1s2, 2s2, 2p6, 3s2, 3p5, with a total number of electrons 17. Okay, the same number. The question is about the element chlorine. Write an equation for the first ionization energy of chlorine. Include state symbols. So what is first ionization energy? The first ionization energy is the energy required to remove one electron from each atom in 1 mole of gaseous atoms to form gaseous 1 plus ions. So we have chlorine gas, then we have chlorine ion, then we remove 1 electron, or just simply that one. So this is the first ionization energy equation of chlorine. Now next question for the same number. Explain the difference in the first ionization energies of chlorine and bromine. Alright, so let's explain the difference of their first ionization energies. So chlorine here, chlorine's outermost electron is in the 3rd energy level, while bromine has its outermost electron in the 4th energy level. Now, the outer electron in bromine is farther from the nucleus and experiences more shielding from inner electrons. As a result, the nuclear attraction between the outer electron and the nucleus is weaker in bromine. Therefore, less energy is needed to remove the outer electron from bromine than from chlorine. While chlorine, the outer electron is closer to the nucleus, therefore less shielding, and high energy is needed to remove the outer electron. Then it has a high first ionization energy. Therefore, chlorine has a higher first ionization energy compared to that of bromine. Right, the same problem number about chlorine. Chlorine occurs naturally as a diatomic molecule. Draw a dot and cross diagram to show the bonding in a molecule of chlorine. Show outer shell electrons only. So it says here that chlorine is a diatomic molecule, which means this is a molecule that is made up of 2 atoms, either of the same element or of different elements when we say diatomic molecule. So how do we draw a dot and cross diagram, or what we call the Lewis structure for chlorine molecule or chlorine gas? So we know that chlorine has an atomic number, atomic number of 17, and its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. So each chlorine atom here has 7 valence electrons in the outermost shell. Now each chlorine atom needs 1 more electron to complete its octet. Octet meaning 8 electrons in its outer shell. Okay. Then each atom contributes 1 electron to form a shared pair, or which is a single covalent bond, and that shared pair counts for both atoms, giving each a full octet. So we use dots for one chlorine's electrons and crosses for the others. So it would look like this. Okay, chlorine, then we have 7 valence electrons. Right. And then another chlorine here. We use crosses. And then one here for the bond. So we have each chlorine atom has 3 lone pairs. Okay. This one, 1, 2, 3, which means 6 electrons in one shared pair. This one. Okay. So this is now the dot and cross diagram of chlorine molecule. Each chlorine atom here has 8 outer shell electrons, which is a stable octet, and the 2 atoms are held together by a single covalent bond, this one here. Yeah. And the molecule, this one is Cl2, chlorine Cl2. So that's how to draw the dot and cross diagram of chlorine gas. All right, the same number. Another question. Chlorine is a gas at room temperature and pressure. Explain why chlorine has a low boiling temperature. So chlorine, or Cl2, chlorine gas, this one is a simple molecular substance. And the molecules are held together by weak intermolecular forces, specifically the van der Waals or London dispersion forces. And these weak intermolecular forces, act only between molecules, not within them, and require little energy to overcome. Therefore, chlorine boils at a low temperature because only a small amount of energy is needed to separate the molecules. Now this question is about hexane, C6H14. The skeletal formula of hexane is given, this one. Draw the 4 structural isomers of hexane in the boxes. So I just didn't include the boxes here. So these are the 4 structural isomers of hexane. So we have 2-methyl pentane, then we have 3-methyl pentane, and 2,2-dimethyl butane, and we have 2,3-dimethyl butane. Now let's draw its the skeletal formula of each of these isomers. So we have pentane. That means it has 5 carbons. So we have 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 carbons, and it has methyl, 1 methyl in the second carbon. Oh my, I should draw it somewhere here. All right. Okay. 2, 3, 4, 5. So let's just draw the methyl here on the second carbon. And then 3-methyl pentane. So pentane has 5 carbons, the same. 2, 3, 4, 5. And 3. So the methyl is attached on the third carbon. So it should be here. Okay. So this one is for the first isomer. This one is for the second one. Now we have 2,2-dimethyl butane. Butane has 4 carbons. So this 1, 2, 1, 2, 3, 4. Okay. 2, 2. So 2 methyl attached on the second carbon. So it should be here. Okay. So this is for the third isomer. And for the fourth one, we have 2,3-dimethyl butane, 4 carbons, 1, 2, 3, 4. And then the methyls are attached on the second carbon here and on the third carbon. So this one is the skeletal formula of the third isomer. Alright, the same question for hexane C6H14. Hexane reacts with bromine in the presence of ultraviolet radiation, so bromine, to form a mixture of bromoalkanes. Draw the initiation step of this reaction using curly half arrows. So in the initiation step of the free radical substitution between hexane C6H14 and bromine Br2, under UV light, the bromine molecule splits or homolytically into 2 bromine radicals. So we have bromine, it splits to 2 bromine radicals. So it's under UV light. So with curly half arrows, we can draw one curly half arrow from the bromine-bromine bond to each bromine atom, showing that one bonding electron gets or goes to each bromine atom. So the mechanism would look like this. Okay, let's change color. So it will be bromine, bromine, and then under UV light, then we have 2 bromine radicals. Then the curly arrows, half arrows, should be here. Alright, so this is the initiation step of this reaction using curly half arrows. This one. So take note that the UV light provides energy to break the bromine-bromine bond, and the bond breaks homolytically, forming 2 bromine radicals. This one, and these radicals then start the propagation steps of the chain reaction. Now the same question and with sub-question, write equations for 2 propagation steps to show how C6H13 Br is formed. Curly arrows are not required. Now let's write the propagation steps in the bromination of hexane. So the first propagation step is we have the bromine radical plus C6H14. This forms bromic acid and C6H13 radical. So this is the first propagation step, and then the second propagation step is we have C6H13 radical, and then we have bromine. This forms C6H13 Br plus 1 bromine radical. So this is the second propagation step, and these 2 steps sustain the chain reaction producing C6H13 bromine or bromohexane. Alright, the same question for hexane. Give the molecular formula of an alkane formed in a termination step in this reaction. So in a termination step, 2 radicals combine to form a stable molecule. So if we have 2 hexyl radicals, C6H13, combine, so it would be C6H13 plus C6H13 radical. These are hexyl radicals. This would form C12H28. So this one is the molecular formula of an alkane formed in the termination step of the reaction. And take note here that the product is larger than alkane. it is C12H28. So we can call this as dodecane. Now the same number, calculate the percentage by mass of bromine in the heaviest molecule containing 6 carbon atoms. Okay, 6 carbon atoms that could form when hexane reacts with large excess of bromine. So how are we going to calculate the percentage by mass of bromine in the heaviest molecule? So the first thing we do is we decide the heaviest possible carbon containing product. So if every hydrogen in C6H14 is replaced by bromine, then we will get the fully brominated alkane C6Br14. So we just replaced the 14 hydrogens with 14 bromine. So now we can calculate the percent by mass of bromine. So we get the molar mass of bromine. So molar mass of C6Br14. So this is 6 times 12 plus 14 times 79.9. So the molar mass is 1190.6 grams per mole. And then we get the mass of bromine in the molecule, which is just 14 times 79.9, and that is 1118.6. Now we can calculate for the percent by mass of bromine. We just have to divide. So that is, okay, I'll be writing here in white. So that is 1118.6 divided by 1190.6 times 100%. And this would give us 93.95%, or approximately 94.0%. So this is the percentage by mass of bromine in the heaviest molecule containing 6 carbon atoms.